Welcome to the third and final section of contributed talks on Maple in education. And our first speaker of this section is Francesco Floris. And she'll be talking about Maple for the development of problem-solving skills in upper secondary school.
Okay, so I share my screen. Okay. Thank you for the introduction. Good afternoon or good morning. I am Francesco Floris, and today I'm talking about our research titled Maple for the Development of Problem-Solving Skill in Upper Secondary School. This research is a joint work with the Professor Marina Marchisio and our colleague Cecilia Fissore from the University of Turin. Our university was founded in 1404 as is one of the most ancient and most prestigious Italian university, hosting about 83,000 students, as is one of the largest Italian university open to international research and training. It carried out scientific research and organizes courses in all disciplines, except for engineering and architecture. This is a picture of our research group called Delta Research Group. Delta stands for Digital Education for Learning and Teaching Advances. And Professor Marina Marchisio is the scientific director of our research group. The Delta group deals with studying cognitive process in digital learning environments that use new technologies, including, for example, Maple, with particular attention to the teaching of STEM disciplines. Among the 8 key competencies for lifelong learning to achieve success are mathematical competency, defined as the ability to develop and apply mathematical thinking to solve a variety of problems in everyday situations, and the digital competence, which presuppose an interest in technologies and their use in critical thinking. Solving contextualized mathematical problem using the software Maple allows students to develop mathematical skills and digital skills at the same time. In particular, problem-solving skills include several dimensions. The understanding, so the ability to analyzing the problematic situation, representing and interpreting the data. The identify dimension, so the ability to model the situation and identify the most suitable solution strategy. The develop to the solution process, so the ability to solve the situation problematic in a coherent, complete, and correct way. And the hardware dimension, the ability to comment and appropriately justify the applied process. The development of these skills, combined with digital skills, is particularly important for upper secondary school students who can be facilitated in a university academic study or in the world of work. The set of our research is a digital math training project, DMT, founded by the Fondazione CRT within the Diderot project and organized by our university. And the first edition of this project took place during the academic year 2014-2015, and in the academic year 2022-2023, there will be the 10th edition. Every year, the DMT project involves about 3,000 upper secondary school students of different schools from Piedmont and Valle d'Aosta in Italy. The aim of the project is developing both mathematical and computer science competencies through the resolution of real-world mathematical problems using the software Maple. The core of the project is the online training, where students learned how to use Maple and solve the mathematical problems every 10 days for a total of 8 problems. During the online training, the collaboration of students it encourages. Student resolution were assessed by university tutor using an assessment grid that you can see in the picture. Yeah, and this grid take into account all dimensions of the problem solving. All dimensions of the problem solving, so understanding, identify, develop the solution process, hardware, and we can add the use of Maple. So our research question is, during a problem-solving activity, how much the knowledge and the effective use of Maple by students contribute to development of problem-posing skills? In order to answer our research question, we have analyzed the students' resolution of the problem during the online training. But our sample is for this research is 60 students of the grade 12 of the 2021-2022 edition of the DMT, so the 9th edition. And the research methodology consists of quantitative analysis of the evaluation of the student resolution at the beginning and at the end of the training to study the correlation between the indicators in the evaluation grid, and a qualitative analysis of the satisfaction questionnaire filled in by the student at the end of the online training. In this slide, we can show a first result that show the difference in the use of Maple between the beginning and the end of the online training. In the first figure, it can be seen how the student at the beginning of the training does not develop a solution strategy including Maple, but use the worksheet as a simple sheet of paper or maybe a simple calculator. But at the end of the online training, in solving the last problem, the student use better the potential of Maple. Let's see, for example, a while loop to check that the condition of the problem are verified, and adequately argues the steps taken and the strategy chosen. For the analysis of the correlation between the various indicators of the evaluation grid, we consider the evaluations of the first and the last problem submitted by the student who delivered at least 5 out of 8 problems of the online training. The correlation matrix shows a strong correlation between all indicators in both the first and the last problems. If we focus our analysis on the Maple indicator and the correlation between this indicator and the others, we can see that from the first and the last problem, the correlation between Maple indicator increases with the indicators develop the solution process here and the hardware dimension. Instead, the correlation of Maple indicators with the understanding and the identify indicator decreases. We can explain this behavior in this way because at an early stage of the online training, students still lack problem-solving skills. So the ability to use the software is more correlated to understanding the problem and identify a solution strategy. At each step of the online training, the difficulty of the problem increases, but also the attitude of the student to solve them. at the end of the training, so Maple skills are more correlated to the development of a solution strategy and to generalization to of the problem, which lead to a better argument for the solution, as we can see in the previous figure. Okay. From the analysis of the responses to the questionnaire, it emerged that students have developed problem-solving and digital skills that they consider useful in the world of work. And students appreciated the evaluations and the feedback from tutors to understand how to improve in solving the problems and using the software to solve them. Okay, in conclusion, we can say that using an H to solve problems favors development of problem solving and digital skills, supporting the whole problem solving practice. These results are useful for understanding the impact of this learning methodology and the use of technologies in the teaching and learning of mathematics. Thank you for your attention.
Thank you, Francesco. That was excellent. We can open the floor to questions now, either in the chat or feel free to unmute yourself and ask. So I'll ask a question. So it sounds like the students appreciate doing something real in Maple using programming, and they feel that that's useful for after their academic career. Can you hear the question?
Not well, sorry. Can you repeat, please?
Sorry. So it sounds like students appreciate doing more than just math. They like doing a little bit of programming in the Maple sheets. Is that correct?
Yes, yes. We can analyze. We had analyzed the solutions from the beginning at the end. It emerged that the average score in the evaluation of the problem is not different between the first and the last problem submitted, for example. But the Maple indicator had a good increase, and the quality of the sheets produced by the student are more sophisticated in the last problem, because they include the potential of Maple for example, a procedure, or not only loop or if-else condition for the solving problems, more better than in the initial phase of the online training. Is normal for us, because in the first phase we had more online lessons to the student to how to use Maple, and during all training, and so during the training they develop Maple skills. So in the last problems they can use the software very better than before.
Great, thank you very much.
Francesco, I have a question for you. I define online as when the instructor is present, whether online or in class, and offline when the student is at home. What is the time split between instructor presence online with the student and the student working by himself offline at home?
We have 1 hour synchronous lesson at week with the student, in which the tutors explain not how to use Maple to solve problems, but in asynchronous we don't have more intervention with the student, because we encourage the collaboration between students. So they have 10 days for submitting the problem, And during this time, they are free to communicate with all students of their grade. So the student of the grade 12 can talk with the Moodle forums principal to all students of the schools participating in the project, and they can develop skills with the collaboration, peer collaboration. So
it is mostly offline.
yes. Online is just 1 hour per week. 1 hour per week online.
Okay, thank you again, and we'll move to the next presentation.
Great. So I'd like to introduce our next presenters, also coming to us from Turin. We have Fabio Roman, Alice Barana, and Valeria Fradiante, and they will be presenting their talk on developing civic education and digital citizenship skills by solving mathematical problems with Maple. So please go ahead and share your screen.
Thank you very much. I am Alice Barana, and with me there are also Valeria Fradiante and Fabio Roman, and we are going to present this paper, which is developing civic education and digital citizenship skills by solving mathematical problem solving with Maple, that we did with Professor Marina Marchisio. Okay. We are also from the University of Turin, and which is one of the most ancient and most prestigious Italian universities. It hosts about 83,000 students, and so it is one of the largest Italian universities. It is open to international research and training, and it carries out scientific research and organizes courses in all disciplines except for engineering and architecture, which are held at the Politecnico. We are, as the author of the last presentation, we are part of the Digital Education for Learning and Teaching Advances research group organized by Professor Marina Marchisio. We are a team of young researchers, and we do research in digital education in mathematics, especially in mathematics and scientific research. And we carry out several research projects for students, secondary school and university students, and in many of them we use Maple. This study involves 30 contextualized mathematical problems to be solved with Maple, which deal on civics and digital citizenship topics. The goal of these studies are to understand how to design mathematical problems with Maple to develop both civics and digital citizenship skills, but also mathematics and problem-solving skills, and how to use how the use of Maple can enable upper secondary school students to develop these kinds of skills. The setting of this presentation is the same than the previous one, but we have a different focus. In fact, the setting is the Digital Math Training Project, which is funded by a Bank Foundation of Turin, and it is organized by our university. It runs since the 2014, so the 9th edition is going to start in the next week. It involves about 3,000 high school students for each edition, and part of them, selected students, are involved in an online training where they are asked to solve 8 problems, 8 real-world mathematical problems using Maple in a digital learning environment where students can collaborate among them. Students are divided in 5 classes based on their age. So they have 8 different problems for each class each year. So in one edition, there are a total number of 40 problems used in the online training. The aim of the project is developing both mathematical, computer science, competencies, but also civics and digital citizenship skills through the resolution of these real-world mathematical problems using Maple. Now I left the stage to Valeria, who will show you the details of this study.
Okay. Our study started from task design. According to Sullivan, task design is multidimensional, and there are 5 dilemmas to face. First one is context, ranging from pure mathematics to semi-reality to reality. Second one is language. On one end, mathematical precision is part of the desired learning, but on the other end, clarity for these students is a need to support the learning. Third one is structure, meaning degree of openness in tasks. And fourth one is distribution, which means selecting content to be focused on in the tasks. At the end, according to Sullivan, the task doesn't exist by itself, but it's important to consider the interactions of the participants, meaning between the teachers and the students. Let's see how we faced 5 dilemmas in our 40 problems. The context is real. In particular, we considered the civics and digital citizenship topics. The language is clear, but a correct understanding of the instruction is a part of the desired learning. In a structure is composed by multiple specific questions in order to provide access for all students who are free to solve all problem or only a part of the problem. In distribution, mathematical contents are established by Italian national guidelines. And at the end, in interactions, in solving problems, students have the chance to discuss with other participants and tutors involved in the project. Let's see an example of our 40 problems called tax code, which is a code of 16 alphanumeric characters, and every citizen in Italy has got a tax code which is quite similar to social security number in USA. So we can see that the topic is about the civics and digital citizenship, and then we gave the instructions to build a tax code. At the end, we ask students to follow some questions. First one is how many Italian tax codes it's possible to generate according to the instruction given before. Or another question is to find a particular tax code for a particular person called Lisa Fassino. So we can see that we design a task with multiple steps in order to provide access for all students. At the end of the project, we asked students involved and their teachers to answer a final survey. And recording civics and digital citizenship skills, students said that they were quite aware of having developed these kinds of competencies, and they said also that these problems were quite useful to better understand mathematics, and also to better face their own career path or their university career. During the training online, teachers of participants of the MT were trained in an optional 6 hours course aimed at showing how to use these problems to engage students in digital and civic citizenship education. They really appreciated the course, and also how these problems help students to develop these kinds of competencies, and also mathematical and problem-solving competencies. In conclusion, we can say that these results could help mathematics teachers develop civic education activities using Maple within their teachings, and encourage them to use an interdisciplinary problem-solving approach to make students develop different kinds of competencies. Thank you for the attention.
Thank you very much for that very interesting talk. Now, if there are any questions, please feel free to unmute yourself and ask, or you can post it in the chat.
Good morning, everybody. My name is Juan Ramirez. I'm from Panama. It was a very interesting exposition. Sorry for my English because it's not fluently. This presentation is very useful for me because I develop videos for citizen education. For example, here in Panama, we have several problems with the pollution of the bay, the Panama Bay. I made a video for education of the citizens about these problems and its solutions. It was very interesting. It's only a comment. Thank you.
Thank you.
All right, so if there are no more questions, we can move on to the next presenter.
Okay, the next presenter is Alexandre Cavalcante, and he will talk on exploring open-ended tasks in secondary mathematics with Maple Learn, the case of functions.
All right. Can I make sure that everybody can hear me well?
Sounds good.
Yes. Okay, perfect. Thank you very much. Hi, everyone. My name is Dr. Alexandre Cavalcante. I am an assistant professor in mathematics education here at the University of Toronto. And I'm joined here today in this presentation by Sisi Feng and Sarah Lu. I hope the two of them can yeah, you can see the cameras of Sisi and Sarah. Hi, girls. This presentation today will focus on some preliminary actions or tasks that we've been doing in our research project in partnership with MapleSoft. This project has been funded through MyTax, which is a Canadian nonprofit organization that provides funding for bridging university and research. And the research team that we have gathered together includes not only me, Sisi, and Sarah, but also Paulina Chin, which is the senior architect at MapleSoft, and Karishma Punwani, who is the director of product management at Maple. The idea behind this project, the reason why we wanted to engage MapleSoft in this project was because Maple Learn was just released a year ago, or almost 2 years ago. And Paulina and Karishma wanted to have some perspectives on secondary teachers and how Maple Learn can support the learning of mathematics through this platform. The foundational framework or the theoretical construct that we used in the project is around the concept of mathematical literacy, which is defined as the capacity to identify, understand, and engage in mathematics to make well-founded judgments about the role that mathematics plays in private life, occupational life, social life. So as you can see, mathematical literacy extends beyond just formal knowledge. It involves a whole spectrum of mathematical domains, not just arithmetic or algebra. And it is also fundamentally connected to real-life contexts. So how have we managed to work with this framework and analyze some features of this platform? We use the idea of problem solving, an ethno-mathematical model of problem solving, in which we always start from a socio-cultural context, a context in our everyday life. And this problem, or some situations in everyday life, can be considered as a problem that needs solutions. And through a formulation process, we can create a mathematical representation for this problem. And only once the mathematical representation has been created, then we employ mathematical procedures, tools, calculations to obtain some mathematical results. Out of this mathematical result, we still need to interpret the results back to reality and evaluate, assess whether the results make sense to our problem. The issue that we faced in this project associated with problem solving is that problem solving, when implemented in classrooms, at least here in Canada, often lead teachers to provide only single solutions to these problems. So mathematical problems have their correct solution or one single solution possible. This idea or this practice can lead to narrow ideas of what mathematical processes can be. Mathematical processes can be used to make sense of reality, more so than providing one single solution. And we thought that open-ended explorations could be one potential solution to this issue by promoting investigation and assumption making in a mathematical situation. So what is the project? How does the project look like? It entails a research internship, which is being conducted by Sarah and Sisi, with the goal of bridging research and industry. So they engage with Maple in this project through both sides. And the project is being conducted in 2 phases. The first phase provides them with the opportunity to become familiarized with the Maple Learn, the platform and its features. And they also have been investigating curriculum trends in mathematics, mathematics education worldwide. The second phase, which we have just launched, entails developing resources for one specific mathematical strand, which we decided to be financial literacy, and also investigating how the features of Maple Learn enable mathematical literacy within that strand. Today in this presentation, we have a limited amount of time. I'm just going to focus on 2 tasks that Sarah and Sisi created while becoming familiarized with Maple Learn. And we try to investigate, or we try to understand some of the features that Maple Learn and how they might be able to enable mathematical problem solving through open-ended tasks. The first activity that we created is called a battleship game, using the different blocks, the different cells that Maple Learn provides within that whiteboard area. Sarah created a game full of different linear segments, and the goal is for students to play in pairs and guess correctly the equation of a linear function that covers those different segments. Okay, so as you can see here, the main portion is dedicated to creating your battlefield, all different segments that will be plotted in the graph. Then the students have a space on the right for some rough work to define the linear equation for those segments. And on the bottom, you see here the students have the opportunity to guess by asking questions to their opponents, what are the linear functions of their opponent's segments. And once they hit all of the different segments, they win the game. The second activity that Sisi created this time is to design a roller coaster. It's interesting because as a mathematics teacher myself, I used to have this context of roller coasters to simply explore quadratics. But in this activity, students have the opportunity to create different piecewise functions that can model the actual design of a roller coaster. So not only the parabolic design, but also the other moments in a roller coaster, moments with less adrenaline, perhaps. And we use here, as you can see, piecewise functions and sliders that can model or can simulate the design of a potential roller coaster. So based on these two activities, what have we noticed in terms of the features of MapleLearn and how this can lead to open-ended tests? The use or the focus that MapleLearn has on the whiteboard and cells, as opposed to focusing on the graphing area, seems to give students the opportunity for rough work, which was one of the terms that appeared in the tasks, and recording their own thinking. So the whiteboard aspect of it seems quite important. Being able to graph segments just by using coordinates, out of these coordinates and segments, being able to graph functions using sliders, not slides here, sliders and plotting points, as well as, most importantly, I would say, hyperlinks that can connect different documents within the platform have shown some promise with regards to open-ended tasks. Specifically, those hyperlinks are important because there needs to be some scaffolding process in an open-ended task, and students being able to navigate through different documents through these hyperlinks was very important. In terms of mathematical content, we've noticed that linear functions and piecewise functions can be explored by looking at different points that belong in a line, being able to determine the equation of a function, whether linear or piecewise, being able to restrict the domain and the image of that function, so you can create segments or create different portions of the piecewise function are also important. The idea of continuity in that graph, specifically through the sliders, seems very interesting because you can see when the slider disappears. And also the assumptions that were made in the design and in the game activities, where students choose which linear or piecewise functions they want to use to create their designs, are very important. Also, through this modeling process, students, they have the opportunity to explore mathematics more authentically and flexibly as well. Now, some preliminary considerations. As I mentioned before, this is some of the considerations based on the first phase of the project. MapleLearn seems to enable, formulate, and interpret, evaluate reasoning processes through the option of recording your own thinking in that whiteboard. And also employ reasoning processes are enabled through the automation of some of these tasks. So when students have to create the equation of a linear function, they don't need to do all that work by themselves. They can use some of these automated processes in the platform that allows them to find the equation of that function more efficiently. Finally, with regards to multiple solutions and verifying your own solution, there's an opportunity here for a lot of differentiation in the classroom. Specifically within that context of the piecewise functions, students can create extremely complex functions or very simple ones. So there's an opportunity in the classroom for differentiation and authenticity. As I mentioned before, as a former mathematics teacher, I was used to roller coasters being simply parabolic. But here we can create complex and authentic models, whether for roller coasters or in a battleship game. That's it. I appreciate your attention. I'm open to any questions. And if you have any specific questions about the design of these tasks, Sarah and Sisi are here. They can tell us a little bit about the struggles to create those open-ended activities. Thank you very much. I think I will stop sharing my screen just so I can see everyone in the screen.
Thank you for that presentation. We do have a few minutes for questions. Once again, you can either use the chat or unmute and ask. I'll ask a question. What is the best roller coaster that the students have designed? Or
That's an interesting question. Actually, we created the activities in the first phase of the project. We haven't implemented them yet, but they are available on the Maple platform in the example gallery. If you just type roller coaster or battleship game, I would invite everyone to try it out at home later and see how complex you can create the roller coaster.
If I may chime in there, I actually did give it as a protocol for a student to try. The best one I would say that a student created was, it was modeled after the Leviathan roller coaster in Canada's Wonderland in Ontario. He literally took it and modeled it exactly for exact. It was so smooth, and everything afterwards, like it was a parabolic. I'm not sure if everyone's familiar with it, but essentially it's a big drop at the beginning, and he modeled it so smoothly, and the ones afterwards were also very similar, but like the scale models, everything was exact. So there's no limits to what you can do with here.
Very nice.
I see one question here. Have you thought of revisiting the roller coaster in further courses, paying attention to smoothness of derivatives? That's one thing that as I was preparing for this presentation, I created my own roller coaster. It did have some vertices, which mean they would not be able to be differentiated. I think that would be a nice expansion, specifically because in the context portion of the platform, we have differentiation and integration options. I would actually be curious to see if it would be possible to do that. Yeah, I can definitely share a copy of the PowerPoint. Well, I think what I would do is I will save and paste it here in the chat while the other presenter is doing the presentation. I think that's allowed, I guess. I'm going to save a copy and I will add it here.
Okay, if there are, okay, there's another comment in the chat. Sisi, do you want to just say that out loud?
Yeah, sure. I was just answering the derivation questions, and I was just saying how like the versatility of Maple Learn is very nice. So I included in that section had to have a subterranean portion, which means it has to go underwater, and then it also had to be connecting in like integers, the point that I connected with. We could totally do it with derivatives as well, in the sense that we can get like, you know, like the slope cannot be too steep, otherwise you can't connect in a smooth curve, etc. And how would you make those connectors like smaller, I guess, or like, it's hard to explain, but like not so like, you know, like reminiscent of a real roller coaster, not too flat, not too jagged edges and stuff like that.
Excellent. Thank you again for the presentation. And I guess we'll move on to the next presenter.
Great. So I'd like to introduce our final speaker for this session, John Pais from Ladue Horton Watkins High School, and he will be presenting his talk on Qubit tensor product circuits modeling Boolean functions. So please go ahead, John.
Thank you. Okay, good morning. Thanks for attending the talk. This worksheet is part of an introduction of quantum computing for high school students who have some kind of experience. They know some linear algebra and computer science, but they don't know any quantum mechanics. What I try to do in this worksheet is to leverage the computational power of Maple to do kind of a guided discovery and exploration of the first few cases of, for example, the Deutsch problem, the Deutsch-Joseph problem. Deutsch problem is just one case, and then use that to try to understand, you know, how to prove those things. So in the third section is where all the technical mathematical material is and the proofs of the corresponding theorems. And we probably won't get to that, but what I want to show you today is just the kind of, you know, my rational reconstruction of this kind of approach. For motivation, the Deutsch problem is really, you know, quite simple. It basically says that if you have a Boolean function from 0, 1 to 0, 1, can you tell whether or not it's a constant function or a balanced function? Yeah, you can, but how many evaluations does it take? With a classical computer, so-called classical computer, ordinary computers, it would take 2 evaluations. So for a constant function, you know, even if we knew the first f of 0 was 0, then we still have to evaluate at f of 1 to decide whether or not it's going to be constant at 0 or so-called balanced. So balance means there's the same number of zeros as n1. Okay, it turns out that if you reformulate this and use a quantum computer to solve this problem, you can do it in one evaluation. And which is kind of one of the exciting things that Deutsch noticed when he first worked on this 30, 40 years ago. I'm not sure how long ago. So the purpose of this worksheet then focuses on 4 problems. The Deutsch problem, as I just mentioned it, and let me maybe make this a little bit bigger. And then the Deutsch-Joseph problem is simply the same problem, whether or not you can determine whether f is constant or balanced when n is greater than or equal to 2. The Bernstein-Vazirani problem is a little more complex. It says that given, you know, a Boolean vector, a Boolean function from 0, 1 to the n, so basically you have n arguments, n Boolean arguments, and you're guaranteed that there exists some one of these, you know, Boolean vectors A, such that the function is described by a dot u mod 2, and that's just, you know, Boolean dot product there. And the problem is to find A. And similarly, there's a problem to find A, but in this case, A is a Boolean vector that essentially makes your function a function that's constant on cosets. And I won't go into that. That if you know a little group theory, you know what that means. Okay, so we're going to do a little background first to show how to transition into using a quantum computer to do this, and then I want to show you some of the computational exploration. So just a couple quick definitions. A 1-qubit state is a unit vector in 2-dimensional complex vector space C2, and a 2-qubit tensor product state is such a unit vector in the 4-dimensional space C2 tensor C2. Okay, actually, these seem scary, but they're not really as scary as they might. If you take a basis for C2 tensor C2, is you just tensor the basis vectors, the standard basis vectors. E0 is 1, 0, E1 is 0, 1. And the way you do that, for example, to do E0 tensor E0 is you just take E0 and quote unquote multiply it times each of its own entries. And then when you do that, it expands out to 1, 0, 0, 0. So that's all there really is to tensor products, including for matrices, you do the same thing. The one really clever thing about this notation, not mine, but is that you'll notice that the indexes of these vectors start at 0 and go to 3, and you can read them off by looking at the subscript. So 0, 0, so you have a 1 in position 0, here's 0, 1. So basically they're binary numbers. So you reinterpret them as binary numbers. So that's 1, and you have a 1 in position 1, and et cetera. 1, 0 is 2, you have a 1 in position 2, et cetera. So that's kind of nice. And that will be used a lot. So what I want to do first, just to lead into this, is to talk about, you know, how in the heck do we map these things one-to-one onto themselves by just changing the second tensor factor, okay? Well, we can just change it. For example, this is the identity, so we don't change anything there on that particular, and the matrix that would do that, if we were to multiply these matrices times these vectors, is just the identity. But we could also just send E0, the second factor, to E1 and E1 to E0. And the matrix that would do that would be one that has an inversion right here. And similarly, we have another one that has an inversion here, and then we'd have 2 inversions. Now this turns out to be a group. That means if you take these 4 matrices, they're closed under matrix multiplication as an algebraic system. I'm kind of going through this a little bit fast. I can see my times. I have a little clock running here, so I need to sort of like speed up a little bit. So the reversible extension now is what we're going to do to embed this function f. We're into something that's reversible, means basically you have, you know, it's going to the function is going to have an inverse, so you're going to embed it in such a way that it's going to be a matrix with an inverse, such as the ones we just described. And the way you do that is you basically just extend little f to capital F, where it's mapping from, you know, 0, 1 cross 0, 1 to 0, 1 cross 0, 1. And the way you do that is effectively you look at the original function and see if it's a 0. If it's a 0, you just, at I, you just have ij, where j is both 0 and 1. So you have I0 and I1. On the other hand, if it's a 1, you flip the bit. Okay. And it turns out that you can apply such a function, such an extension, to the subscripts of these basis vectors, and everything works out really nicely. Here I have, like, in gory detail, how this works and the correspondences between these various things. And you can see here that if f0, if f is a constant function equal to 1, right, then we get, the 2 inversions and basically evaluate those to show that really works with those vectors. And then if it's a constant function equal to 0, then it's just the identity. Okay, so that's just a little bit more interesting detail there. And now I need to speed up a little bit. Okay, so in order to write a program for a quantum computer, you need to write it in linear algebra. And this diagram basically is code for that. So essentially what you have is your input on this, you have a qubit state here that's an input on this line, and you have another one here that's input on that line. But basically what you're really doing is you have E0 tensor E1, that's going to be your input, and then you're going to multiply it times the matrix you get by tensoring H and H. And that's down here. And then you're going to multiply the next one by one of your X2 matrices, X2A, B, or C. And then finally, you're going to decode the output and measure it. Okay, so I'm just going to go through this a little bit fast. So that's what effectively what's going to happen. And here we're doing this. I'm just going to recreate this group. And so it's C2 cross C2. It's a 4 group. And then I'm going to basically, have a few methods I've created here. Apply, notice this applies from right to left. So we take this matrix, we multiply times E0 tensor E1, then the next one. So we can do this down here. And you can see that what happens, so I'm showing each application, they're going the other usual order from left to right. So that's X1 times E0 tensor E1, then X2A, then X3, and then the final output product is this. So you'll notice that in this case, we can factor out an E0 in the tensor product, and that's really crucial because that means we can measure, right, on this qubit, we can measure this qubit and determine that we got with probability 1 that basis vector, or that qubit is in that state. It's in the state E0. And so that corresponds to the constant function. And similarly, we can do the same thing for the balance functions. And for the balance functions, we get E1. And yes, there's the other balance function. We also get E1. And then for the constant function equal to 1, we get E0. Okay, so effectively, we can determine by one evaluation and a measurement in this complicated setting, that whether or not we have a balanced or a constant function. And I'm still checking my time here. Okay, so if we just organize this, we can see, oh yeah, that's what we have. And there are other interesting things that have to do with counting the number of balance functions. That's going to be, in general, basically we have 2 to the n arguments in our domain, so it's going to be 2 to the n choose to the n minus 1. In this case, it's simply 2. Now this is the case for n equal 2 and 3. So for n equal 2, we just add another Hadamard gate here. Our y2 is going to be here. These matrices get really big. And I'm just going to, without actually, I'll just show you the code here. We do the same thing, and it turns out that, we are in a position where, we're able to factor out a 1, 0, or a 0, 0, or et cetera. And we have a similar situation, I won't be able to discuss it all here, in which case we have our 2 constant functions and we get an E00 factored out, right? And then we have our balance functions, E01, et cetera. And those all correspond to the even permutations. So the matrices that are even permutations, and we have odd permutations. So now we're in a position where basically some kind person has to give us a function that is balanced or constant, and then we can determine whether or not it is that. Because we now have a whole lot of other functions, namely the ones corresponding to these odd permutations. And you'll notice that in this case we have a linear combination of all the basis vectors, and so that's one case we can eliminate. Okay. So now if we boost this up to n equal 3, So what do we have? We have 2 cubed domain, right? So that's 2 to the 8th. So we have 256 matrices, right, that correspond to those functions. And so if you do that, what I have done here is, so there's a lot of stuff, right? There's a lot of examples. And so what I've done here is I've used Maple to sort these into the number of output basis vectors in the output. And then I'll also to use the trace of these matrices to determine which ones are balanced. Okay, so you can see that. Here's example, this is count 1. So effectively what we have, you can see the trace is 16. So what that means is, yeah, that's the constant function equal to 0. And then here's a trace 8. You can see that we can factor out 1, 1, 1. And so that's going to be, you know, another one of our balance functions. And then you'll also, if you look at this, you'll, you know, see that, you know, everything is really cool in the sense that, you know, we have 14 balance functions and we have 2 constant functions, you know, for the output number of basis vectors equal to 2. However, you know, that's not all of them, right? In this case, what, you know, there are, the number of balance functions is 8 choose 4, which is 70, right? So there's a whole bunch of them that appear when the number of output basis vectors are 8. Okay. And so in fact, yeah, there are 56 there. Gee, 56 and 14, that adds up to 70. That's wonderful. Now, what you can do is, and part of this motivation here, which I'm not, you know, I'm rushing on, I apologize for that, is you wonder, okay, now how do I distinguish? How do I distinguish? Come on. How do I distinguish, you know, the situation from the nice factorization and the not so nice factorization? So if you look at, you know, trace 8, so this is trace 8. And if you look at this a lot and look at these vectors and say, gee, how do I determine, you know, whether that's going to be a balance function or not? Well, it turns out that if you look at this carefully, you can see that there's no way you can factor out a 0, 0, 0, E000. It doesn't appear in any of this output. So that could give you a clue that that's what you should do to approach the proof of this. And so then, and sorry for rushing through all this, but just I'm almost going to connect this up here. It turns out that let me just read this. In the Deutsch-Joseph problem, if we assume that there's black box that evaluates our function little f, we conveniently assume that f is either constant or balanced, as I said before. Then by 1 and 2 above, we can determine which type of function we have for arbitrary n. Okay, so it turns out that what happens here is you can prove that there isn't, that the coefficient of E0n for the balance functions is always going to be 0. So that means you will get the same distinction if somebody conveniently gives you, you know, both a collection of balanced and constant functions. Okay, I think I pretty much used up my time. I apologize for running over if I did.
We're running ahead of schedule, so you can continue a little bit.
Okay,
longer.
thank you very much.
Nope.
Okay, so it turns out that what we do is we prove this main theorem, and I'm not really sure who it's due to, because none of this, as far as I can tell, is written up, you know, in precise mathematical detail. It's somewhere, I'm sure. You know, there's Nielsen's explanation is pretty darn good, but I'm not sure where there's a real, you know, complete, you know, like understandable by a student version of this. But at any rate, this is the kind of, you know, main theorem that we use that has to do with putting the reversible extension in 2 forms. So what I call the standard reversal circuit 0 and circuit 1. And circuit 1 is one I use for the Deutsch-Joseph problem and also for the Bernstein-Vazirani problem. Okay, and circuit 2, let's see, yeah, circuit 2 or circuit SRC 0. I think that's right. Well, I have to prove another theorem because in the in the Simon problem, you have to extend so that the domain is multivariate too. So there's a little bit of work there to extend that, but that's what we use. Pretty much the same setup generalized to each of the component functions, right? I'm sorry, this is very sketchy. But at any rate, it turns out in the Simon problem, you have to run it several times and you don't really get, you know, and actually in order to do that, it's order n, it isn't immediately one evaluation. But you still, get an exponential speed up. Finally, let me just say that also for completeness, I include the standard Boolean gates. So you can see how to use this construction with the standard Boolean gates. And it's really simple and straightforward. Effectively, you have circuits that look like this. And so the subscripts correspond to, that's like, for example, for an AND gate, that's false, false, and false, and false. If they're both inputs are false, you get false. If one is false and one is true, you get false, etc. One is true, one is false, you get false. And then finally, yay, when they're both true, you get true. And similarly, you just change this last qubit state to E1, and you can get the NAND gate. Okay, thank you very much for your attention. I appreciate it.
Thank you, John. That was very impressive. Are there any questions from the audience?
Just a question to John. So the audience that you're usually going in, do they have a lot of computational background or more mathematics or
yeah, usually the students I teach, they're pretty strong. Our strongest students that take calculus 3 vector calculus and usually in sophomore or junior year, and they take several computer science classes starting as freshmen. And so yeah, they're strong. They don't know a lot of mathematics, but they know linear algebra. We do linear systems in vector calculus, and so they have some exposure to linear algebra and also some exposure to linear algebra used in computer science to do various things.
Yeah, it's a great intro to the quantum kind of computations. Yeah, great stuff.
Thank you.
Okay, are there any other questions? If not, then I believe that concludes the final Maple in Education session for the 2022 Maple Conference. So thank you everyone for attending. And